Okay, yeah, I'm now sharing the visualizer and I'm turning it into full screen. Okay, so this can make us see a bigger screen, I hope. Is that right? Can you see it better or is it the same as before? Good, okay, great. So today we're going to continue our discussion about the 4 modes of convergence. And I know this is a little bit abstract, so I'm going to give you a quick recap again before we continue. So about the 4 modes of convergence. So the simple way to put it is that for the first mode, convergence in law, or so-called convergence in distribution, here we are only concerning the CDF, the distribution function, and not really the actual realization of xn or the limit x in a sequence. So we don't care about the realization, each realization. We only care about the overall distribution of each xn and each x. So that's why here the joint distribution of xn and x is not a concern for the convergence in law. And for the convergence in probability in the Rth mean, and almost surely, they all concern about the joint distribution. But there are some actual differences. So the 4th mode, almost sure convergence, is what is closest to the convergence of a real sequence, of a fixed sequence. So if you think about it, it's actually saying that if we consider a realization sequence, that is, we have a sequence of real numbers and the real limit, then that sequence must converge to that limit. And we want this to happen for all the realizations. So it's a sequence by sequence by sequence. For every realization, we want the convergence, right? That's the almost sure convergence, and it's the closest to the real number convergence. So that's why whenever you have some doubt, just think about this as the real number convergence, and that will become easier. And for the 2nd and the 3rd, they are not really about a convergence of a realization. They are talking about convergence on an average sense. By average, I mean across realizations. So it's just a different way of average. So here in the convergence in probability, we are not concerning the actual values of xn. We're just concerning whether xn is in an absolute neighborhood of x. So as long as it's out of the neighborhood, we just count it as a violation. And then the probability is the average proportion of violation. So we want this average violation proportion to go down to 0 as n goes to infinity. That's it. And here, we're not just considering that violation, we're actually evaluating the absolute difference between xn and x and raise it to the rth power. So the r is fixed. For example, it could be 1, it could be 2. And so it's something you predetermined, you assigned. And then given the r, you evaluate that difference between xn and x using this absolute difference raised to the power r. And then we calculate the average of this difference that is across the realizations. So we want this average difference go down to 0 as n go to infinity. So basically realizing that 2 and 3 are about average across realizations, not a particular realization, you can see how we can construct counter examples so that we may have them, these two converge, but the last one doesn't converge. And similarly, we may have the last one converges, but these two don't converge. And that's the counter example we gave last time. And I'm going to show you this. If you recall, this is a counter example to show that we do have convergence in probability and convergence in Rth mean, but we don't have almost sure convergence. The reason is that by our construction, if you still recall this example, we are having alternation between 0 and 1 in the sequence. So you see that depending on, for the realization, depending on the realization of Z, so depending on where Z lies in, we will always have 1, 0, 1, 0, 0, 0. So for these two numbers, x2 and x3, only one of them can be 1. The rest is 0. For those four numbers, 4, 5, 6, 7, only one of them can be 1. The rest are 0. So what we will expect is that as we go down and down into the sequence, we will encounter 1 less and less frequently. But there will always be a 1, no matter where you are in the sequence. So this is a clear violation of almost sure convergence, because for every realization, that sequence, that real sequence, is always having 1 somewhere. So using the language we saw last time in the Bureaucratic Lemma, this means that we will have 1 infinitely often in the sequence, right? So therefore, with that alternating, we will not have every realization, no realization will converge. So we will not have almost sure convergence. However, we look at the average, either in the probability, in the violation here, violation, which is about the probability convergence, or in the arith mean, we can see that both of them are going down to 0. And here's what we said. Here it is. The reason is that when we talk about something in average, we are good since we only encounter 1 less and less frequently. So that's why this probabilities go down to 0, and the average difference is also going down to 0. So that's it. This is the first famous counterexample, and I want everyone to really understand this so you can understand the distinction between convergence in probability, convergence in arith mean, and almost sure convergence better. Okay, the second example here, this is something I made a mistake, but I want to make a clarification. So here, this sequence, we're constructing it based on still a uniform z. And given where z lies in, the xn can take values. Okay, so basically, as long as z is in this interval 0 to 1 over n, our xn is taking a non-zero value. It's actually 2 to the power n. So it increases super fast. And here I made a mistake because here, you see, what I'm saying is that z is 1 over 32. I said x5 is 0, but that's not right. So it should be, I'm going to make a correction here. It should be x32 is 0. And before that, actually, x31 in the second realization, this will actually be 2 to the power 31. So it's getting very, very large until z is no longer in the interval 0 to 1 over n. So you see, it will suddenly drop down to 0. So by our construction, you can see that as every realization will finally get down to 0 and then stay at 0, we do have almost sure convergence. Every sequence converges. However, because before the values go down to 0, it's getting super, super large, 2 to the power n. That's why we do not actually have the expectation going down to 0. So that is, we don't have the arith mean convergence. So you understand the differences, right? The arith mean convergence is not just about a particular sequence, it's about all the sequences, all the realizations you look together on average. Since there must be some super large value in one realization, that will blow up the expected difference. But if you look at every particular sequence, yes, you will see convergence. So that's why there's some differences here. And I think this difference is quite interesting. Okay, that's the two examples. And then we have this, okay? We talk about this relationship. We're saying that convergence in law doesn't imply convergence in probability. We can find a counterexample by having xn and x independent, right? We have that. So when they're independent, we may have convergence in law, but not convergence in probability. And we use the first counterexample, that alternating one, to violate, okay, convergence in probability does not imply convergence almost surely. Convergence in arith mean does not imply convergence almost surely. And using that last example, we show, okay, convergence almost surely does not imply convergence in Rth. That's it. So we have all these relationships that don't hold. And then for the red arrows, we're saying that these are the things that can hold. So almost sure convergence does imply convergence in probability, and convergence in Rth implies convergence in probability. Convergence in probability implies convergence in law. So today we're going to continue this discussion. All right, so we first want to talk about why almost sure convergence would imply convergence in probability. So to do that, we introduce an alternative definition of almost sure convergence. That is this. Okay, so we're saying that you see the difference between this one and the convergence in probability. The key difference is that in convergence in probability, we're just talking about xn and x. And we're not talking about xn plus 1, xn plus 2, etc. in this one realization, in one particular realization. But here, when we have this almost sure convergence, we're talking about one particular realization inside this probability. That is, when we have this non-violation, we're not just talking about xn itself. We're talking about xn plus 1, xn plus 2, and up to x infinity. So all the things after xn, we want all of them to be within the epsilon neighborhood of x. And you see, this is also aligned with the definition of convergence for a real sequence, if you recall, right? For a real sequence, if we say, okay, the sequence is convergent to a limit, we want to say for every epsilon, we can find an n. Then all the elements after n will be within the epsilon neighborhood of the limit. So this is aligned with that. And so that's why you see, given this definition, then the proof is quite straightforward. So at almost sure convergence imply this. And you see the probability of this is actually smaller, or actually I should say this. So the probability, maybe I should say it another way. So basically this thing, the probability of this is actually greater or equal than the probability of this, right? So maybe I should pick a new paper and write it. So let's going to show this. So we want to first prove 4 gives us 2. That is the almost sure convergence implies convergence in probability. And why is that? The alternative definition of almost sure convergence gives us the proof, basically. So we have for any epsilon greater than 0, okay, and we have the probability that xn minus x less or equal than epsilon. This probability is larger or equal than the probability that xk minus x is less or equal than epsilon for all k greater or equal than n. You see, this is a more stringent event than this one, right? So whenever this happens, this happens. So that's why this probability is greater than this probability. And we know that this one goes to 1 as n goes to infinity. And this is because we have xn almost surely converge to x because of this. Then we're done, right? So then we have shown that this thing, because this thing is controlled under 1. So we will have this thing converge to 1 as n goes to infinity. So we have xm converges in probability to x. That's it. So this is a quite straightforward result mathematically, but if you really think about why this happens intuitively, you need to think about the realizations we give. So here it means that in every realization, we have the sequence converge to the limit. And then in probability, right, what this means is that we look at the nth point and we look at on average, what is the proportion of violation. Because of this convergence, we can have that proportion of violation go down gradually to 0. So that's why we have the convergence in probability. And so essentially, this almost sure convergence happens within every sequence will ensure that the violation probability, which is this one, is, or this is not, this is the reverse of the violation probability, but we want to have the violation probability, this becomes greater than, that will converge down to 0. Okay, that's the first result. And for the second result is about 3 implies 2. So that is, if we have the convergence in the rth mean, we have convergence in probability. I'm also going to talk about the proof for this part because I think it's a very, very useful technique. It's actually Chebyshev's inequality. I think many of you have learned this in a probability class before. So it's actually a way to relate violation probability to the expected differences to the rth power. So what I mean by this is that if we write down what we need from this one, right, the convergence in rth mean, we look at this expected rth absolute difference between x,n, and x, right? We have this go down to 0. And for this one, you know, we can always find a lower bound for it. How do we do it? It's actually this. We just introduce an indicator function. That is, we can write it as the absolute difference raised to the rth power times the indicator function that xm minus x is greater than epsilon. You see, this inequality always holds because this indicator function is binary. It's either 0 or 1. When it takes 1 for sure, then we will have this thing stay as it is. When it's 0, then it becomes 0. So that's why this number is always less or equal than this number. So that's why taking expectation is still less or equal than. But what is the advantage of doing that? You see, by doing that, you know, okay, this number will take value 0 if the indicator condition doesn't hold. That is, if this number, xm minus x absolute value is not greater than epsilon, then this becomes 0. And therefore, we have a lower bound for this part when this is non-zero. And this part is actually epsilon to the rth power. So essentially, oh, sorry, I think, yeah, that's fine. So essentially, I would have correct. I will have this part as epsilon to the power r. Then it's a constant. I can get it out of the expectation, and then I get expectation of an indicator function. This is another very useful technique in probability. That is, the expectation of an indicator function is equal to the probability of the event in the indicator. So this becomes epsilon to the power r times the probability, that is xm minus x greater than epsilon. And that's it. Okay, so basically, this inequality is actually this is how we can derive Chebyshev's inequality. So if you check that, you will see Chebyshev's inequality is just a special case where r equals 2. So with this, we can actually have an upper bound on this violation probability. So I'm going to write the probability the thing is less or equal than, I'm just going to write less. Okay, expectation xn minus x to the power r divided by this. Okay, and as we know, this part is going down to 0 as n goes to infinity, right? And this part has a lower bound 0. Then we're done. So then we have xn converges in probability to x. That's it. And I can also give you the intuition why this holds. If you think about the definition of the convergence in arith mean, it's regarding the average absolute difference raised to the power r going down to 0. And that one is actually more, I would say it can take larger value for the absolute rth, absolute difference, for the expected rth power of absolute difference. This number is actually bigger than the violation here, right? The violation is only about what proportion of my xn is outside of my x neighborhood, epsilon neighborhood. So this number is actually bounded between 0 and 1, but there's no bound for this one. So you can imagine that this is more difficult to satisfy than this one, and when this satisfies, this one satisfies. Okay, so this is exactly what we're reflecting here, right? If you can have this part bound going down to 0, then this part will go down to 0. That's exactly what I was saying. Okay, so the take-home message is that convergence in almost surely is more stringent than convergence in probability. Convergence in the arith mean is also more stringent than convergence in probability. So that's why in statistics, we often rely on convergence in the arith mean to help us prove convergence in probability. We also utilize convergence almost surely to help us achieve convergence in probability. Because as I said, ultimately, what we are mostly interested in are the first two modes, convergence in distribution and convergence in probability. And convergence almost surely, convergence arith mean are what we use as our techniques. And why do we want to introduce convergence almost surely? The reason is its similarity to the real number convergence, because we have so many techniques from the real analysis about the convergence in numbers. That's why if we can utilize them here, that can make things easier for us. That's why we want to learn those. Okay, the last result about the important one is about convergence in probability implies convergence in law.
Professor,
that is. Yes.
Excuse me. Just before you do the next one, I'm curious, there's the epsilon to the r power in the denominator, and that I would think makes this bound, like, or this inequality really, really not tight. Are there any examples where the expectation is equal to the probability and so it's kind of tighter?
Exactly, this is not tight. Yeah. So if you're interested in this, there is a whole wide range of topic about how to find a better upper bound on this. And so that is called the concentration inequality. So that's a pretty big topic in statistics. So if you want to find a better bound on this, we call this concentration inequality. And so we have better ones like the Hofstad's inequality. So Chebyshev is simple, but it's not really a tight one, as you said. Yeah, exactly. So it's like for different upper bound on this, you will have a different form. Like for Hofstad's, you actually get an exponential term. But in the Chebyshev, you just have the moments. Yeah, because of, like you said, a wide range of statistical theory is regarding how an estimator is concentrated on its parameter value, right? And to evaluate that, you use those concentration inequality to bound this violation. And that's a central topic.
Thank you so much.
Yeah. Okay, great. So from 2 to 1, we have this convergence in probability implies convergence in law. Okay, and for this one, essentially, we're just trying to prove the CDF convergence. Okay, so basically what we want to prove, the key idea of the proof is that, so for any x0 where the CDF fx is continuous at, we want to show that this fxn at the x0 is convergent to fx at this x0 as n goes to infinity. So we are just trying to do this. And we know that the technique we can use to prove this is to use that violation probability, this one, going down to 0. And that's because we have convergence in probability. So we basically want to utilize that to achieve this. And the key idea is this. So I'm not going to write the complete proof, it's in the notes, but I'm going to give you the key idea. The key idea is that for this left-hand side, it's actually equal to the probability that xn is less or equal than lowercase x0. That's the definition of CDF. And we want to see how this might be related to something here, you see. So if we think about the one-dimensional case, but this proof can hold for xn being d-dimensional or p-dimensional. But here we're just going to talk about one-dimensional case. So in the one-dimensional case, if we think about it, let's say x0 is here, right? And we're interested in what's the probability xn is less or equal than x0, the probability of the left-hand side. That's what we're interested in. But how about x? Okay, here is only xn. How about x? We know that xn and x must be quite close to each other when n is large. This is because of the convergence in probability. So in other words, we can have a relationship like this. So I'm going to write it down and you can think about it. The relationship is xn less or equal than lowercase x0. I call this an event. This event, when this happens, this must happen. One of these two events must happen. That is x less or equal than x0 plus epsilon, and, or I should say, or x minus xn is greater than epsilon. So what I mean is that, so whenever my xn is somewhere here, okay, and my x is in its epsilon neighborhood, so you can imagine. So this is like epsilon, this is xn minus epsilon, xn plus epsilon. So whenever x is in its epsilon neighborhood, what would happen is that x can at most reach here. That is x0 plus epsilon. Think about the sliding window. This is where my, if this is where my x lies in, whenever this window moves, and when xn directly reaches this point, then here's my x. Here's the upper bound of my x. It cannot go beyond that. Otherwise, x would be away from the epsilon neighborhood of xn. So that's why one of them must happen. And this is implied by this. So what this means is that as long as this happens, this event happens, then this union of two events must happen. So you can explore this idea geometrically by plotting the relationship. That's it. Okay, so basically from this, using this relationship, we can actually find an upper bound of this. And I'm going to write it as, so the probability xm less or equal than lowercase x0 is less or equal than the probability of the union is also upper bounded by the sum of the probabilities. The probability that x is less or equal than x0 plus epsilon plus the probability that xn minus x is greater than epsilon. So now you see my intention. As n go to infinity, this term will go down to 0. And I can have this less or equal than that. And epsilon is something I can decide, right? Epsilon is a fixed small number. I can make it as small as possible. So you see, I'm getting close. I'm basically bounding this one by this part. And similarly, I can write a second side. So similarly, I can write the probability of xn less or equal than x0 minus epsilon. I'm shifting epsilon to the left-hand side, and then I can write it as less or equal than probability x less or equal than x0. Okay, plus, oh, my bad, sorry. I should write this. This is one thing, x and x0. I swap those two, and we'll see that. Plus probability xn minus x, this one. This is what I need, the two sides. You see, our goal is to find an upper bound and a lower bound. And what I can do is that I can let my epsilon go down to 0 so that this part is becoming this CDF. This part is becoming this CDF, and this part is also becoming this CDF. So I'm getting a sandwich to put this part, the CDF of xn, in the middle, and I'm done. So that's just the technique we used here to show the convergence in CDF. And later, when we start talking about, probably next lecture, when we start talking about convergence and law, we will have more techniques to prove that. So for example, we can use the convergence of the characteristic function to prove the convergence and law. So that's a more widely used technique. But here we are using the basics. That is just the definition of the convergence in law. Okay. So those are the most important results I want to say about the relationship between those things. And there are also some very interesting relationships that we put it in the notes. It's called the Theorem 2.10. So it's about some partial relationships, but it's not exact. So you need to add more conditions to make them exact. So it's actually here. So if we come back to this page. So we are done with this, right? So we have this, this, and this, and we cannot go the other way. But there are some actually exceptions that allow us to or special cases that allow us to make some of those crosses hold. Okay, and here we're going to give you some examples. So the first one is about a special case. So I'm going to talk about it. So this, I'm going to use a dashed arrow to mean that this may hold in special case. The special case is if xn is converging in law to a constant vector, not a random vector or random variable, but a constant, then we have convergence in probability to the constant. That's the first result. So it doesn't hold in general for any limit, but for constant limit, this does hold. And you can think about it, why? Because when this limit is a constant, then there's no longer any joint distribution, right? So because only xn is random and the limit is a constant. So what the argument we said about, okay, the convergence in law doesn't imply anything about the joint distribution, that no longer matters because the limit is no longer random. So that makes things a lot more easier. That's the first important result we want to say. about the partial converse. Okay, and so for this one, we're not going to prove it. You can check the notes, but the basic idea, and in the notes, we prove it for 2 dimensions. And the 1-dimensional proof is actually even more straightforward. So basically, let me write the key idea. The key idea is to write this thing. The key idea is to write the probability xn minus x greater than epsilon. We want to express this, sorry, my bad, C. Yeah, we want to express this in terms of the CDF, the fxn. So basically, you're going to use this, and that's it. Just, you can check the notes and you will see why. Okay, this is the first partial converse. The second partial converse is regarding the almost sure convergence and the convergence in Rth mean. So we said that almost sure convergence does not imply convergence in Rth mean. And recall that example that we have the value here rising to in the rate of 2 to the power n until it suddenly drops to 0. That example we just showed you, right? So you see, the reason why that example is a counterexample is because even though we do have almost sure convergence in every realization, but in every sequence, before it goes down to 0, it undergoes an exponential growth. So it's like exponentially growing and then suddenly drop down to 0. That's where the issue is, right? So therefore, to be able to fix that and let 4 implies 3, the intuition is that we need to give it an upper bound on that sequence. So we cannot let it grow too fast. Okay, so here it is. So if xn converges almost surely to x, and we have xn to the power r is upper bounded by a random variable z with expectation of z finite. So this thing need to have a finite expectation. Then we are fine. We have xn converges to x in the Rth mean. So you see, what we add, the condition we add to fix this cross is by bounding the Rth power of the absolute sequence by another random variable and restricting the random variable's expectation to be finite. So you see, this is a direct way to remove that counterexample we gave you. Because in that counterexample, if you just do this thing, you can see that you will not be able to find the z as an upper bound. That's it. Okay, so if you want to check the actual proof, this one will rely on what we call the dominated convergence theorem. So I'm going to talk a little bit about it, dominated convergence, after we finish our discussion here. Dominated convergence theorem, short as DCT. So we'll actually give you 2 important theorems later. One is called monotone convergence theorem, then the other is dominated convergence theorem. So these 2 theorems are basically about how you can use almost sure convergence to imply the convergence of some expectation. And that's exactly what we mean, because the convergence in the Rth mean is regarding the expectation. Okay, so this is about this partial relationship. So the key thing is that I think you can compare this result with the counterexample we give, and then you will see why it is so important to give an upper bound on this. Okay, and the third partial converse is regarding, so it's still regarding this thing, but it's about, so it's still from 4 to 3, but it's from using a different perspective. Probably I can say it here. It's like a special case. So still about this, but it's another special case. So this one actually has a name. It's called Chevy's useful convergence theorem. So it's actually from the measure theory. And here we're talking about special case and from 1947. So in this result, what we're saying is about R equals 1, okay? It's specific about R equals 1. So what it says is that if we have almost sure convergence and we have non-negative sequence, okay? And we have expectation of xn converge to expectation of x. And this expectation of x is finite. We have all the three conditions. Then we have xn converges in R equal to 1 in this specific Rth mean to x. That's it. So for this one, I just want to make a clarification about the difference between this and this. And that's what I want to say. So I want you to realize that this one is not equal to this one. Okay, and this is what we mean by convergence in Rth mean. This is not. You see, what's the difference? Still, think about the realizations. That can give you a better idea. So in terms of realization, you see, what we're doing is that for every realization, we calculate the difference. And so let's say we have capital B realizations and we have capital B differences, we take the average. That's the right-hand side. And on the left-hand side, we're not doing that calculation within a realization. Instead, this is the average across realization, and this is the average across realization. So basically, the two things can be not coupled. So for example, I can give you example. So here, I may have xn as 1, 2, 3, and x as 3, 2, 1. So in that case, you see the expectation of xn equals the expectation of x equals 2. That's what we'll have here. But if in the case here, in this example, you see the expectation of, still the same example, expectation of xn minus x is what? It's actually 2, 0, 2. So I have 2, 0, 2. And that will actually give me 4 over 3. So you see, even though these two are equal, this is not 0. That's exactly what I mean. They're not the same thing. So that's why, you see, having this does not imply this. We will not get from here to here. But if we have the almost sure convergence, and we also have a lower bound, 0, and then these things together will give us the result we need, the convergence in the Rth mean with R equals 1. Okay, so if you're interested in this, we basically are, so this is actually related to, if we talk about the convergence in function, then this is actually related to saying that, okay, if you have a function converges pointwise, how can you get a uniform convergence of the function? That's exactly the general case of the Chevy's theorem. And if you are interested in this, you can check the notes for the details. So I'm not going to talk much about this because I think this one is not so commonly used in our later lecture. So I'm going to skip this part, but it's good to know. And I think if you're interested, you can check it. Okay, that's the third partial converse. And the last partial converse is regarding how we can go from convergence and probability to almost sure convergence. So right here, this thing. We have a cross here, we say this doesn't go here, but we can say something special about the subsequence. So this is about 2, 2, 4. And what we're trying to say is that, So this thing, xn converges in probability to x, is equivalent, or we say if and only if, every subsequence n1, n2, and so on has a subsequence. We write m1, m2, and so on, such that we have x and j converges almost surely to x as j goes to infinity. That's what we want to say. So basically, even though we cannot say this whole sequence converges almost surely to the limit, but we can say of for any subsequence you give me. So for example, you can pick the subsequence as 1, 3, 5, 7, 8, 1, 3, 5, 7, 9, etc. So in any subsequence you provided, I can always pick a subsequence within your subsequence so that this thing, the subsequence, will converge almost surely. And to help you understand why this will hold is to think about that counter example we give. If you recall that alternating counter example. So in that example, we have 1, 0, 0, 0, another 1, 0, 0, 0, 0, another 1, right? We have that one. So you see, in that's a typical case where we have the convergence in probability, but not convergence almost surely. But you may wonder, what if when I pick the subsequence, I just arbitrarily avoid touching those later ones. I just pick those later zeros. Then I can have convergence almost surely. That's the intuition exactly. We can choose how to pick the subsequence mj based on any subsequence index you give me. So this is a very general statement. And you may wonder, why do we want this? The very important motivation is this. That is, we can do things in two directions. So I'm going to give you an intuition why this result is important. Why do we need this? Again, the reason is that it's easy to work with. It's easy to work with the almost sure convergence because of our analysis techniques. So what we mean is this. So I can give you the logic. So suppose that we want to show, so if we want to show xn converges to x, right? So by this, we just need to show the right-hand side. For any subsequence, we can pick a subsequence to have almost sure convergence. We just need to show x and j converges almost surely to x. Oh, sorry, my bad. I want to say this, okay? So if anything, we can say this. Okay, yeah, exactly. This is right, we want to show this. But how do we show this? So suppose we have, say, yn converges almost surely to y, and we have xn as gyn, x as gy. So, and the g is continuous, a continuous function. So for example, we have a sequence converges almost surely to a sequence, but we want to show whether, and we want to have its transformation, a continuous transformation. So the thing that is nice about this almost sure convergence, this is from analysis result. That is, if you have a sequence converges to a limit, then if you apply a continuous transformation to every number in the sequence and the limit, then the transform sequence will still converge to the transform limit. That's it. So here we will have this nice result, that is xm converges almost surely to x. So we can easily apply this. And then you see, this is why this result is very useful. So as long as we can show that a subsequence converges almost surely to something using some technique, we can restore the convergence in probability for the whole sequence. And that's what we need for our statistical analysis. So basically, again, as I said, our goal is to utilize convergence almost surely to help us prove convergence in probability. All right. So
I have a quick question. Sorry.
Yeah.
So do we just need to show for like one subsequence converges, or do we have to demonstrate that every subsequence?
Okay. Yeah, so basically we want to show that for every, exactly, we want to show that for every subsequence, no matter which subsequence you pick, within the subsequence, I can always find the subsequence that converges almost surely.
Okay.
Yeah,
Gotcha.
so for example, if you only show for one subsequence, that's not enough. For example, if you can show, okay, in my sequence, x2, x4, x8, x10 converges almost surely. But what if I give you x1, x3, x5, x7? Then it doesn't hold, right? So I must find a subsequence within your x1, 3, 5, 7, so it converges. That's what we need.
Got it. Thank you.
Yeah, thank you. Okay. So, and if you recall, last time we talked about the Bureaucratic Lemma. That is why we need it here. So Bureaucratic Lemma is the key for us to prove this equivalence. So from the left-hand side to the right-hand side is actually, okay, so from the right-hand side to left-hand side is actually quite trivial. So I'm not going to, I can just quickly say it. Okay, from the right-hand side to the left-hand side, let me put it here. So this side is trivial. So let's first show this. So for this direction, we will just use a counter proof. So what I mean is that we want to show if xn doesn't converge in probability to x, then we cannot satisfy the right-hand side. So that's the argument, right? So if B implies A, then not A should imply not B. That's the argument we're using here. Then what happens is that when this happens, right, then there exists some epsilon greater than 0 such that we would have the probability xn minus x greater than epsilon larger than delta for infinitely many n. We're directly writing the counter argument of convergence and probability, because you see in convergence probability, the definition is for any epsilon greater than 0, we can have this thing, we can find a delta such that this thing is less or equal than delta for all the k larger than this n, right? Here we're writing the other side. That is, there exists one epsilon so that we will have violation of this infinitely often. So we cannot find an n such that after this n, all the sequences contained in the epsilon neighborhood. We cannot do it anymore. In the delta neighborhood, we cannot do it anymore. So because with this, then you see, we can find this for infinitely many n, then we will not have convergence almost surely for any subsequence, because if you pick any subsequence, you will always encounter violation. That's the case. So no subsequence converges in probability, so not almost surely, right? If a subsequence cannot converge in probability, it cannot converge almost surely. That's for sure. That's also implied, because almost sure convergence implies convergence in probability. So we're using that counter argument for twice in this proof. You can think about it through after the class, but that's basically the counter argument we're using. And this hand side, the other direction, from left to the right, given a convergence in probability, for every subsequence, within that subsequence, we can find a subsequence to converge to almost surely. For that one, we need to use Bureaucratic Lemma. So essentially, we want to look at this event. So this is the event we're interested in. This xm minus x greater than epsilon. This is the event we are interested in. And so basically, what we want to say is that, so if we want to have almost sure convergence, what do we need about this? We need to actually add one more thing. We should say this thing happens infinitely often. This event is actually having probability 0. Has probability 0. This is what we mean by almost sure convergence. Okay, so exactly it's like the Bureaucratic Lemma we gave you at the end of our last lecture. What we mean is that when this happens infinitely often, it means that if we go down a sequence and across the realizations, we will, actually I should say within every realization, we will have violation. And if we look at across realizations, we will see violations occur infinitely often, no matter how large n is. No matter how much we go down the sequence, we still encounter that violation infinitely often. And this is exactly what we mean by not convergence, not almost sure convergence. And if we have this event with probability 0, then we have almost sure convergence. So essentially, what we need to pick the subsequence is that, so our goal becomes to, so our goal is to pick a subsequence mj such that we have this event xmj minus x greater than epsilon infinitely often. We will have this thing with probability 0. Okay, and then here is the Bureaucratic Lemma. What can do? We are going to use the first statement of the Bureaucratic Lemma. Let me try to remind you from our last lecture notes. This is what we're going to use. You see, because we want this infinitely often event to happen with probability 0. So we just need to make sure that the sum of the probabilities of events is finite. As long as we can pick a sequence of events such that their probability sum is finite, then we can say, okay, these events happen infinitely often, has probability 0. That's how we're going to use the Bureaucratic Lemma. So here is something we could use the convergence in probability to help us. So basically, what I do is this. So here's the strategy. What we do is that we pick epsilon 1, epsilon 2, etc., such that I have the summation j from 1 to infinity epsilon j finite. I intentionally pick these numbers to achieve this. And one famous example or one easy solution is you may set epsilon j to 1 over j squared. If you set epsilon j to decrease in this way, then you can satisfy this finite sum, right? So that's one strategy. You can find other ways like j cubic inverse. So with this, then you have a sequence of epsilon j's already, right? And then you want to utilize that convergence in probability to help you pick the subsequence. Okay, then we have, then find mj such that you would have the probability xmj minus x greater than epsilon j less than epsilon j. You can just pick the probability in this way, right? So basically, given the epsilon j, I can always find somewhere in my sequence, the index, such that this number, this probability is less than epsilon j. Then I can find this is guaranteed by the convergence in probability I have. So this is guaranteed by xn convergence in probability to x. I have that. So then, you see, I'm almost done. So you see, I define the event. I'm going to use the Bureaucratic Lemma. I define the event aj as this. I define as this. Then you see, I have the summation j from 1 to infinity, probability aj. This is less than summation epsilon j by this, and that's finite. So I have it. And then by Bureaucratic Lemma, statement 1, I have that. I have this probability that aj occurs infinitely often has probability 0. Okay, and that's it. That's it. So this is equivalent to saying, okay, the probability that xmj minus x greater than epsilon j infinitely often has probability 0. And this is actually for what? We can actually have, so we have this for epsilon j, right? We're not done yet. But what the last step we just want to say is that here, since the epsilon j is going down to 0, so we would have, since epsilon j is going down to 0 as n goes to infinity. So essentially, what we can say is that we have, for any epsilon greater than 0, we can have the probability xmj minus x greater than epsilon infinitely often. And this probability is still 0. Because you see, I can always find, I can always find some epsilon j smaller than my given epsilon. Then see this epsilon just going down to 0. So I can always find some epsilon j after or lower than this epsilon. And then for those epsilon j, this event will happen. So you see there's some connection between these two things. And then I'm done. So this is just saying, okay, this subsequence xmj is converges almost surely to x. So I'm proving it for picking a subsequence. So how about if you give me a subsequence and I pick within your subsequence, then still the only difference is that when you give me a subsequence, then when I find this mj, I'm having some constraint. I can only find mj within your subsequence, but still the argument just carries over. It's just like if you didn't specify, you just gave me the whole sequence, I can pick mj with more choices. But if you give me a constraint subsequence, I just have to pick mj within your subsequence, but still the argument just follows. So the intuition behind this is saying that even though we have counterexamples to show that, okay, we have convergence in probability, but every realization has that oscillation so that we do not have the convergence almost surely. That's our counterexample. But within that realization, you can always pick a subsequence to get around from those oscillations. So in your picked subsequence, you do have almost sure convergence. That's the intuition. And so the strategy for using this result is that in practice, if we want to prove something in probability, it may be easier to prove that there are some subsequences. For subsequences, you can show, okay, it converges almost surely. So it's easier to show. You can pick a subsequence to show convergence almost surely. And if you can do that, then you have convergence in probability. So that's how this result might be used. Ultimately, we are still more interested in convergence in probability in statistics. So that's all I want to say. So this concludes what I want to say about these 4 modes of convergence. But before we finish this lecture, I want to give you some brief introduction to what I said, the monotone convergence theorem and the dominated convergence theorem. Okay, so these two are very important results to know. So the first one is monotone convergence theorem. So this one is regarding, and let me put it here. Okay, so and the other is dominated convergence theorem, DCT. So both of them is trying to give you conditions about what? So they are both trying to give you conditions about how you can go from xn converges almost surely to x to expectation of xn converges to expectation of x. So both are conditions for this argument. And you see that even though it may seem, okay, this convergence in expectation is easier than almost sure convergence, but it may not be the case. It may not be the case. So just as we have seen in the counter example, where we do have almost sure convergence, that is, we have that exponential rise and sudden drop to 0. In that counter example, we have almost sure convergence. But because of the unboundedness of every sequence, because of the unboundedness, we actually cannot even have this. The expectation may still blow up. It does not converge. So that's why you see the intuition to ensure this is that we need some bound on the xn values. And that's why this and this happens. So the intuition is to bound xn. That's the case. Otherwise, even though we have almost sure convergence, the expectation may still blow up. Okay, so then what are their actual statements? So for the MCT, the statement is that if the sequence is monotone, then we're good. Monotone and non-zero. So if we have 0, and xn converges almost surely to x. So if we have these, then we have expectation. So monotone sequences are always easier to work with. So you see, the reason why monotone is a good thing is because you are not going to have the case where, as we have seen in the counterexample, that a sequence rises and drops to 0. So that is not allowed here. If it rises, then it always rises. And then it has that almost sure convergence, you see. So basically in every realization, it has a limit and it's monotone. So you see, monotone and having a limit, both things actually guarantees that your realization numbers will not go crazy and expectation will not blow up. That's the intuition behind the MCT. And we use the 0 to provide a lower bound, so we will not worry about the negative explosion. right? We only worry about positive sequences. That's the MCT. And the DCT, okay? The DCT is to provide a bound. So that's this. So if we have xn almost surely converges to x, and we have absolute values of xn bounded by y with expectation of y as finite. So y just guarantees that expectation will not blow up. And here the xn can be negative or positive. So we just bound its absolute value. Then we have expectation of xn converges the expectation of x. So the DCT is a more general case, right? But we prove DCT from MCT. So MCT is just a simpler one to prove. And with MCT, DCT becomes provable. So you see, DCT doesn't have the non-negativity constraint, and it's just more general. So in practice, we use DCT as long as we can find the variable y, and we're done. So if we can find a variable y has an upper bound on the absolute value of the random sequence, and the y has finite expectation, that's the only thing we want. So this is a very, very useful way to think about things, right? When we work with a sequence of random variables, we actually want to find the upper bound. That's just one random variable. It doesn't change with the sequence. And this is actually guaranteeing that the expectation of the sequence will not blow up. Okay, so basically what I'm saying is that MCT is going to prove DCT. But in the middle, we have something that we need, and this is called the Fatos Lemma. This already is also in the notes. So Fatos Lemma is a very important result that can allow us to go from MCT to DCT so that the proof can carry over. And what does Fatos Lemma say? So we're running out of time, and this is also not the focus of this class. So I'm just going to give you a very short idea. So what Fatos Lemma is saying is essentially a generalization of this result. That is, the expectation of the minimum of random variables is less or equal than the minimum of the expectation of random variables. That's the essence of Fatos Lemma. So if you take the minimum first and then expectation, the expectation will be less than if you take expectation first and then take the minimum. So by generalization, we mean that essentially we are replacing this. So in Fatos Lemma, we say basically we're replacing the minimum by the length. Right? So if you're not familiar with the length, what it says is that it's the asymptotic lower bound of your sequence. And this is less or equal than length of expectation of xn. That is Fatos Lemma. Okay? So basically, that's it. And so a very simple way to understand what length is, if we have a sequence that changes like this, but then it stabilizes this, then this upper part, this is what you call length. So even if the sequence may not converge, but if it stabilizes and the length is just the limit of its lower bound. And that's so basically every sequence can have a length, but it may not have a limit. That's just a very, very short way of introducing this whole thing. But I'm saying that the MCT, DCT, and the Fatos Lemma, these are more advanced materials for the students who have the time and the interest to learn more. But they're not really directly related to the four modes we talk about. So we basically just need DCT for some proofs. And in order to prove DCT itself, we need MCT and Fatos Lemma. So these are proof techniques and some foundations. So starting from next class, we're going to move on to talk about convergence in law specifically. And I think it will be easier. So we have already gone through the most difficult part of this class, in my opinion. And this is about the probability foundations. So from then, we are going to talk about convergence in distribution, mostly, yeah, in this class. So that's all for today. And so for those of you who might have joined late, so we have a seminar announcement. Let me see, I'm going to quit this. We have a seminar announcement posted to the group, and that will be at 11. So if you're interested, you can attend it. So I'm going to just send this again in case some of you haven't seen. Yeah, this will be the link for the Zoom. And also, please, if you're interested, just copy the Zoom link. Otherwise, once I end this Zoom call, the message will go away. Okay, so if you have any questions, yeah, we have an office hour today from 1 to 2. And yeah, so any questions are welcome. And then I'll see you on Thursday. So see you then. Bye.
Thank you.
Bye.